Okay then, welcome to the webinar on automatic tuning of structured controllers using the Modeling Toolkit and JuliaSimControl. I'm Jay Jagdish. I'm a part of the marketing team here at JuliaHub. A little background on our presenter, Dr. Frederick Carlson. He leads the JuliaSimControl systems team here at JuliaHub. He holds a PhD in automatic control from Lund University, and he has 10 years of experience in the fields of modeling, control, system identification, and robotics. During the course of the presentation, if you have any questions, please enter them into the chat and he will answer it. Okay, over to you, Frederick.
Thank you, Jay. All right, welcome everybody. Today, as Jay said, we will talk about automatic tuning. And we will talk about tuning of structured controllers in JuliaSim. And there are two interesting words there. First, what is JuliaSim? So we all know about Julia, the programming language, being a fast and modern language suitable for technical computing. And JuliaSim is a platform built on top of the Julia programming language that allows us to leverage the power of Julia for modeling, simulation, and control purposes. So the problem setting we will explore today is obviously we want to control something, right? It's a talk about controlling, tuning controllers. And the controller is structured. So what does that mean? So very often we find ourselves in a situation that we need to tune a controller. Maybe it's a controller for a electrical motor, for some processing plant, for an HVAC system, and so on. But we can't select the controller structure arbitrarily. We don't have full freedom there. So maybe we would like to use an LQR controller because we have learned about LQR from university. But the control system, the physical hardware is already outfitted with a control system. Maybe the electrical motor comes with a PI controller or PID controller, and that's what we have to work with. So that is a structured controller. It has certain parameters. It's part of an overall block diagram, and we can't select how this block diagram works arbitrarily. But we have to tune the controller nevertheless. And there might be some design criteria. So for instance, we want to achieve some robustness, we want to achieve some performance, and so on. And that's something we will dive into during this talk. So let's see if I can navigate here. So how do we solve such a problem in JuliaSim? The first step is to have a modeling toolkit model. And modeling toolkit is an acausal modeling language, which means that you model your system using equations rather than input and output blocks. And the main benefit of using equations is that you can model reusable components. So you can have a library out of components that such as transistors, capacitors if you work in the electrical domain, or links and joints and inertias if you work in the mechanical domain, and you can puzzle those together and the modeling tool will figure out how to simulate it for you. Once we have such a model, we would add something I call an analysis point, and that's essentially like a name of a signal. So if you think of a block diagram of your system, the analysis point is a name attached to one of the lines connecting different blocks. We will dive a bit deeper into that during the talk. Then we specify objectives. So what do we want our system to achieve? We call it tuning objectives here. And then finally, we solve an optimization problem, and that's the automatic tuning part. So today we will look at this example. And here we have a block diagram, and there is a lot of different boxes here, and we will try to break them down. So on the far right here, we see a motor. So we can think of that as an electrical motor. Maybe it's part of a robot joint. So a robot has several different joints typically, and each of those are controlled by a electrical motor. So all the physics of the system belongs in the motor block here to the right. And then to the left of the motor block, we have three blocks called labeled KV, KI, and a differential operator here. So the joint coordinate, the position coordinate of the motor is labeled Q here. That is fed through the differential operator and produces the velocity. So this is the velocity of Q. So this two blocks, KV and KI, they implement a PI controller for the velocity. So we have one loop here, the inner loop, that is a velocity loop. And then if we look at the outer loop, we have a KP. So that's a proportional controller for the position. So this would implement a cascade controller with an outer P controller and an inner PI controller. And this is a highly structured controller. It has, we can think of it as having two different inputs. It's really, we can measure, typically only measure positions, but maybe we measure them with a very fast sample rate so that we can filter in a very high sample rate, and then we can pretend that we actually have two measurements. So this is a system with two measurements, but a single input. And we realize the controller by this cascade structure. So we would like to tune KV, KI, and KP in this block diagram today. So what's an analysis point? I said that we can think of it as a named signal. So if you look at this block diagram here, I have given some of the signals here names. I have labeled this one Q, and here is Q reference and Q dot reference. So dot denotes the time derivative. So this would be the reference of the velocity. So if we attach such names to our signals, we can refer to them later. So here we have some ModelingToolkit code. I start by loading the library ModelingToolkit, and I load the standard library with block diagrams. Then I create an input and an output, and I connect them together. And we see when I do that, it just prints connect. It's just a connection. So this corresponds to one of the lines in the block diagram. But if I add a symbol here in the middle, the symbol name here, and I form that connection, we see that instead of a regular connection, it's now printed as an analysis point. And it's given a name, and it's between two signals. And the reason it's the middle argument here, it's to signify that this name doesn't belong to either the output or the input. It rather belongs to the connection between them. All right, so this is what we need to be able to refer to signals for control system tuning in our model. All right, let's move to the next slide. Now I load the JuliaSimControl library. So this is part of the JuliaSim suite of tools. And I call the function control demo systems.dc motor. So this function already defines the DC motor with the inner PI controller. So we see that this gives us a model with 61 equations, and it has a number of different states. Actually, it has a large number of states, maybe more than what we would expect. And that's okay at this stage, because we will perform compilation of this model, and after that, we will have the number of states we might expect from such a simple system. And we see there are a number of parameters here. There are 25 parameters, and we can see among those parameters, we have things like PI controller.gain.k. Okay, so this would be the proportional part of the inner PI controller. And similarly, we have an integrator, and that also has a gain. So these are the two parameters we are interested in tuning as a first step. We can ask about the equations of the system, and here I've drawn a simple block diagram again, so it's easy to refer to. And here we see that among the 81 different equations, we have a number of different analysis points here. So we have the analysis point Y, and that's at the plant output. So this is the measurement from the motor. We have E, this is the control error. So that's the difference between the reference and the output. So this would be the error here. That is what is fed into the controller. And then we have a control signal called U, which is the output of the controller and the input to the plant. All right. The next step on our journey towards tuning this controller is to specify what parameters do we want to tune, and what ranges do they have, are valid ranges for those parameters, and in what operating point do we want to tune this controller. So I would like to say that any parameter can be tuned. Today we will talk about tuning controller parameters, but we could, in theory, also tune plant parameters, and then we would call it plant and controller co-design. So that's perfectly fine. There is no difference between control and plant parameters in this case. And the operating point determines where the optimization solver will try to linearize the plant to compute things like sensitivity functions, gain margins, phase margins, all of these robustness measures that we are used to. And in this case, an operating point include states, inputs, and parameters. And that's perhaps a bit different from what we are used to thinking about an operating point. Usually we only include the state variables and the inputs in the operating point. But there is a very good reason that we include also parameters. And we will get to that in the end of the webinar. So in code, this might look something like this. I start by calling the function complete on the system. So that means that I'm done building my model. And this allows me to refer to the internal parameters of the system a bit easier. Then I create a list of tunable parameters. So this is just a vector. And each entry in the vector is a pair that maps the parameter to an allowed range of parameter values. So we say that the proportional part of the PI controller, it's allowed to be somewhere between this very small number and 100. And similar for the integral gain of the controller. And then I specify a list of operating points, right? So in this case, I just use the default specified in the model, and I have a single operating point. But if I have a complicated nonlinear problem and I would like the controller to work well in many different operating points for my nonlinear system, I can include a list of operating points. And crucially, if I have some parameters that are unknown or I'm a bit uncertain about some parameters, I can include several different operating points to make sure that the controller works no matter what instantiation of my parameters I have. And that's something we will see towards the end. But for now, we have a single operating point. So let's run that and move forward. Yeah, this system is actually linear, almost linear. So one operating point is sufficient for now, but we can imagine doing this also for nonlinear systems. Then it's time to specify the objective. What do we want our control system to actually do? Maybe we want it to track a reference accurately, or we want to have a short settling time if we perform a step. We don't want it to sway. So if we make the robot move from one point to another, we don't want it to shake too long time. We want it to stand still after a while. We don't want too large overshoot when we make a step response. If we have a disturbance, we want to reject it fast, perhaps. We want to have large gain and phase margins. We don't want to amplify measurement noise. So we know that our controller is basing its input based on a measurement. And if that measurement is noisy, then the input will also be noisy. And if we send a noisy input into a robot, for instance, the robot will shake and it will destroy maybe the gearboxes in the motor. And we want to be robust in general towards or against model uncertainty. So this is a model-based procedure. We make use of a model of the system to tune the controller. But we know, of course, that the model, we can't trust it. It's not going to be perfectly accurate to the real world. So we want to make sure that we are robust with respect to that uncertainty and it works even though we have some small model mismatch. So we might want to actually achieve all of those objectives or a combination of them. And many of them are competing objectives. It's very difficult to be both extremely robust against model uncertainties and be very fast at the same time. You can't really have both. You must have a trade-off. But we certainly want to have a little bit of both, right? We want to be not too slow and not too non-robust. We want to be somewhere in the middle. And that's the job of the control engineer, to figure out what is the appropriate trade-off. So here we see an example of a reference tracking tuning objective. I specify a natural frequency or a kind of a desired bandwidth, and then a desired relative damping of a second order system. I then create the transfer function. So this is just a simple second order transfer function. And then I package this into something called a step tracking objective. So I say my reference model is gref. This is how I want my system to behave roughly. I have a certain tolerance. I don't require it to behave exactly like this system, but roughly within 20% maybe. And the response I want to behave like gref is the response between my reference and the output. All right, so here are the analysis points come into play. So this is the name of one of my analysis points, and this is another one. All right, we can plot that to see how it looks. All right, so here is my desired step response. Looks like a reasonably well done second order system. And on the next slide here, we actually have some formulas, but I don't want them to scare you away. We're going to break them down. So we're going to talk about something called a sensitivity objective. And the goal with that objective is to shape something we call the sensitivity function. And this allows us to promote both performance and robustness. So maybe you don't remember what the sensitivity function is. If we look at this block diagram, the output sensitivity function happens to be the transfer function between R and the control error. So if we send a bunch of frequencies in here on R, the sensitivity function will tell us how do those appear in the control error. And ideally, we want the control error to be 0. We want the output to perfectly well track the input. And that's realistic if this is changing slowly. But we can't expect, if we want the robot to move infinitely fast, we can't expect it to do that, right? So we can't push down the sensitivity function everywhere. And the transfer function for the sensitivity function in this block diagram, it's 1 over 1 plus PC. You might be recognize. And as I said, it's the transfer function between the error and the reference. If we look at the peak magnitude of the sensitivity function, so if we plot the Bode curve of the sensitivity function and we look at the peak, that's what we call the age infinity norm of the sensitivity function. I call that MS. And we usually want to limit that. We don't want it to become too large. And the reason is because this is related to the classical phase margin phi m and the classical gain margin. So if we have a too large peak in the sensitivity function, we will have a small phase margin and a small gain margin. And we typically want them to be reasonably large so that we are robust with respect to uncertainty. All right, so there is good reason to limit this peak. So we can look at an example of a sensitivity objective. The way I shape it is by providing a transfer function. And then I pack it into a maximum sensitivity objective. And I say I am interested in the sensitivity in the signal Y. So that's at the plant output. And if I plot that, it looks like this. So we have some kind of forbidden region here in red, and we want the real sensitivity function to be below this forbidden region. So for low frequencies here, this is frequency on the x-axis, the label has fallen off. We want to have a very small value for low frequencies. So that means that if we have a slowly varying reference, we will have no error. But if we have a very fast moving reference, we will have some error because we can't really act too fast. But crucially is that we don't allow too large of a peak. So this function will always level out at 1 for high frequencies. But if we are not careful and we push the performance of the system too much, we might have a large peak here, and we want to avoid that. So this kind of gives a nice trade-off between performance and robustness. All right. We can have other classical design criteria as well. So we can limit overshoot and specify a desired rise time or settling time or something like that. So we can have an overshoot objective. We can have a rise time objective. So here we have a certain time on our hands until we must be above a certain value and so on. And the same for a settling time objective. Here we also have a certain time, and after that time we must have converged within this tolerance here. So for today's demonstration, I will not use these objectives. I will just use the step tracking objective, maximum sensitivity objective, and the settling time objective. So I put the objectives I'm interested in using in a list or a vector. So now we see we have 3 different objectives here, and they are printed in a nice way here. All right, so now we have pretty much everything we need to create an auto-tuning problem. The last thing is to define a frequency grid and a time grid. So here I have a grid of logarithmically spaced frequencies between 10 to the power of 0 and 10 to the power of 3, and I have 200 of them. And I have a time vector where I want to evaluate time responses. Now I can create this structured auto-tuning problem. So all of the things I've created in the previous slides, I just pass them in here. And we see that I have an auto-tuning problem with the model DC motor, and these are my objectives, and these are the tunable parameters. So remember, we're only tuning the inner PI controller for now. All right, so we can plot that problem. We haven't yet solved it. We just plot it based on the default values of the controller parameters. And we see here that we do a quite poor job at following this step tracking reference, and we have some violation here in the sensitivity function. The peak is a bit too high. And also we are violating the settling time here. It's swinging too much, right? And it takes too long time to settle down. So that's not good, but hopefully after we have solved the problem, it will look better. All right, so now it's solved. I will break down what's done here. Here is an initial guess for the parameters. If you don't specify one, it will use the default parameters in the model. So I just call solve of the problem, and then I specify the solver. You don't have to specify that, but I do that so I can get verbose output and see. We can see that it takes a number of iterations here, but it's fairly quick. And now we can plot the result. And now we see that we do a better job at following the step reference here. We are satisfying the sensitivity objective. We are no longer violating the peak here. And we see that we are almost satisfying this settling time objective. We see we have a very slight violation here. And I want to bring up this because in general, these objectives will be competing. So we can't do infinitely well on all of those. So the solver will try to do a compromise between satisfying all of them. And here it's hard to know if we are satisfying this because we gave some tolerance, 20%, right? But here it's very obvious that we are satisfying this objective. And here we have a very slight violation. So if we would have made this tuning objective tighter, more difficult, and we tried to push this down even further, then we would have clear violations of the objectives because it's not possible to satisfy them. So that can happen. We can also look at the status of the objectives after we have been tuning. We see 3 numbers here. So in this case, the step tracking objective has the largest number. That means that this objective has been the most difficult one to satisfy. So if we want to tune our objectives, maybe we would like to take a look at this objective. All right, so now we have tuned these 2 blocks, KV and KI. And now I will add the outer loop here with the KP for the position controller. And previously we just loaded this model from the library, but now we will actually see some ModelingToolkit code to assemble the outer part of this block diagram. So remember, we have a number of summation nodes here labeled sigma. We have a feedback node, and we have a proportional gain here. And we'll try to identify them in the code. So we start with the inner system. That's the DC motor from before. We have a reference. It's a step change. So this is just a signal that goes from 0 to 1 at time 0. We have a derivative to compute the derivative of the reference for the velocity feed forward. We have an summation node, so that's one of the nodes that were labeled sigma in the block diagram. Here is our proportional controller. It's just a gain for a simple P controller, and so on, right? And then we have a bunch of connections. So each connection here forms one of the lines in the block diagram. And here we see I add an analysis point here. So this is my reference. It's between the output of the reference and the input to this identity block. And similarly, we have a number of analysis points down here. And I package all of this into an ODE system, my connections and all the inner subsystems. And when I do that, I get the model with even more equations and state variables than I had before. All right, so now I do more or less the same thing I did before. I specify my tunable parameters. These 2 parameters, I had them also last time, but now I have also the proportional gain for the position controller. I still have only a single operating point. I specify a step tracking objective, and this time it's for the position loop. And maybe you don't remember, but this is slightly slower because typically we want the position loop to be have a lower bandwidth than the velocity loop. And then I have a new maximum sensitivity objective here. I package my objectives into a list, create a structured auto-tuning problem, and then I call solve on that problem. All right. And it's done. And yeah, we can't really see the printout, but we'll just go to the plot instead. And here we see now how the outer position loop behaves. So we are roughly following our reference step, and we are satisfying the maximum sensitivity objective here. All right, so now we have successfully tuned what I call a structured controller. But this was a very easy case, and we will try to make it even more interesting for you. So what if we have a parametric uncertainty? What does that mean? Maybe in our model we have a number of parameters. So in a motor there is parameters determining how much friction is there in the motor, what's the inertia of the motor, what's the inertia of the load that the motor is driving. Perhaps there is a flexibility in the shaft of the motor that creates resonances and so on. And maybe we are uncertain about some of these parameters. We can't find a data sheet where those parameters are. Maybe the inertia of the motor is in the data sheet, but the inertia of the load is perhaps not in the data sheet. And we want the controller to be robust with respect to such uncertainty. And we can indeed do that. So to do this, I have implemented some helper functionality. So here I load a package called Monte Carlo measurements. And I say that I want 5 samples. And then I create an object called particles. So this particles object, it behaves just like a regular floating point number, but it really represents kind of a distribution of values. So in this case, the distribution is uniform between 0.015 and 0.025. So if I create that object, we see it's printed as a mean value with some standard deviation. But now I can use this value. I can do arithmetic with it. So I can add 2 and square that. And that produces a new number with a new uncertainty. All right, so I can use this to communicate to the optimization problem how uncertain I am about my parameters. Yeah, I can also plot the uncertainty. So in this case, it's just a uniform distribution. So this just means that I'm a bit uncertain about this J parameters, and this happened to be the inertia of the load. All right, so here I do exactly the same thing once again. I get my operating point is the default of the model, but I say that the operating point, this is a dictionary that maps parameters to values. I say that the value for this inertia.j is my uncertain j I created in the previous slide. Otherwise, everything is exactly the same here. And when I call solve this time, it takes a bit longer time. There it's done. Let's go to the plot. Now when I plot it, we see that I have not 1, but 5 curves in each plot. So the optimizer has now tried to satisfy all my tuning objectives for all instantiations of the uncertain plant. And this you can do this not only for one parameter, you can have multiple uncertain parameters and so on. And we should keep in mind that obviously the computational requirements scale. If you add too many uncertain parameters, it might take a while. But for this 5 parameters, I can run it again. We see it's still fairly quick. So no worries there. But this is really a powerful method to be able to achieve a robustness in a different way than the classical gain and phase margins. So the gain and phase margins are there for us to be robust against uncertainty. But that's kind of an unstructured, diffuse kind of uncertainty. Well, the gain margin is not very diffuse. It tells you how much the gain of the system can vary. But here we can allow any arbitrary parameter of the system to vary. In this case, we vary the inertia. And if you remember from an harmonic oscillator, maybe the simple pendulum, we know that if we vary the inertia, we vary not only the gain, but also the pole location. So we get different resonance frequency. And we can see that in the sensitivity function here, that the peak occurs on different frequencies. So this parametric uncertainty is really an intuitive but powerful way of modeling uncertainty. And we can become robust with respect to that kind of uncertainty here. All right, so I would like to summarize what we have seen today. We have done automatic controller tuning, and today we did only controller tuning, but we can actually also tune plant parameters using this. We have modeled our objectives, such as reference tracking, sensitivity, maximum sensitivity, maximum settling time, and so on. And we have optimized so that our control system will meet those objectives. And then we, in the last step, we modeled uncertain parameters and made sure that our control system was robust with respect to that uncertainty. So today we have seen a functionality that is self-contained in JuliaSimControl. And if you are interested in recapping this webinar, we can go to the documentation. You find it at help.juliahub.com. And that takes you to a page that looks like this. And on top here, there is a tab. Maybe I make this a bit larger. A tab labeled control. So here you can find an introduction to the JuliaSimControl library. But crucially, you can find, if you go to, so this is not yet released. We need to go to the development version. It's in an upcoming release. And we have a look under controller auto-tuning, tuning of structured controllers. So here you find everything I have been talking about today. And if we scroll down, we see exactly this example I've been going through today. So this functionality is self-contained in JuliaSimControl, and it works with ModelingToolkit. But if you would like to extend this, so maybe you would like to add your own cost functions, maybe you would like to optimize a particular simulation where you follow a very intricate trajectory and so on. You can do that also. And the way we do that is by interacting with Model Optimizer, which is a different part of JuliaSim. So Model Optimizer is a framework for tuning arbitrary parameters in a ModelingToolkit model in much more complicated situations. So you might have data sets, you want to fit model parameters to data and so on. But we can use this also to tune controller parameters in slightly more complicated situations. And then you can make use of the tuning objectives we have seen today and add them to your optimization here as well. All right. Last thing.
We have some questions. Would you like me to ask you later, or?
Let's see. I can have a look at the questions here. Can we use the toolkit for plasma particle simulation? So my answer there is unfortunately that I do not know. I have no familiarity with plasma particle simulation, but ModelingToolkit is a language for modeling and simulation. So I encourage you to go to the documentation on ModelingToolkit and have a look at some of the tutorials there. In particular, we can model PDEs, ODEs, DAEs, delay differential equations, stochastic differential equations, and so on. So there is a pretty decent chance that you can model your problem there, but I cannot promise you, unfortunately. All right, and then we have, since objectives are competing, do we change one to a constraint if it must be satisfied? So that's a very good question. You can determine how strict you are with a certain objective. And by making the objective strict, the optimizer will try to satisfy that at the cost of the other objectives. And if it cannot meet that objective, you can certainly specify objectives that are impossible to meet. And then the optimizer will fail in that case. But certainly you can specify how strict you want different objectives to be. Are we able to mix a discrete controller with continuous plant? Yes. Okay, thank you for that question. The current answer is no, but ModelingToolkit has very preliminary support to actually do that. Currently, it's not in a usable state, so I wouldn't recommend you to actually use it unless you happen to be fond of tinkering, right? So ModelingToolkit is open source. It's there for you. It's not documented, but you can find it if you look for it. But I would envision within a couple of months, we will have that support much more well developed. And then certainly you can mix discrete and continuous time systems as you would like. All right, and we have, what is the asymptotic scaling for number of parameters? Are we using a joint methods to calculate? Yeah, okay, thank you for that question. I'm not exactly sure what asymptotic scaling is. I would assume that, so we use forward mode automatic differentiation. So that will scale linearly with the number of parameters. And then there is some non-trivial scaling with the number of parameters in the optimizer, which might be slightly more theoretically than linear, but in practice, I often see a sublinear scaling. So my answer is that it kind of varies and it's problem dependent, but it's not order n square at least, because we can make use of sparsity and things like that. So yeah, problem dependent, but I tried just for fun, right? Here I sampled 5 parameters. I can say I sample 500 and see how it works. Yeah, it works. Yeah, I have to wait a minute maybe, but it works. So it's not a problem. All right, that were all the questions that have appeared in the chat. If anyone has additional questions, I encourage you to write them there.
Yes, I see that someone raised their hand. Would you please type your questions in the chat, so in the Q&A panel, so Frederick can answer it?
In the meantime, I would like to promote our YouTube channel. So I've been working the last couple of months recording videos. So some videos are tutorials using our tools. Other videos are basic learn control with Julia. And we intend to release one such video each week. And the first video is supposed to come up just in a couple of days, I think. So check out our YouTube channel, in particular the modeling and simulation playlist there. And if you would like to learn how to use the basic control theory tools in Julia, and also how you would use our more advanced tools that build on top of the basic stuff. All right.
We don't have any more questions.
Yeah, okay, a question appeared. Is JuliaSimControl compatible when solving ODE with ModelingToolkit? Or can it be integrated with your ODE system, which is solved with classical discretization methods? So I'm not entirely sure what that means. ModelingToolkit is just a model compiler. So what ModelingToolkit does is it allows you to write your model. And then when you are done, it performs compilation of that model. So it performs model compilation steps like pairing and alias elimination and things like that. And then it will write a code, Julia code, that is the right-hand side of your DAE in general. So for simple systems, it will be an ODE, but for complicated systems, it might be a differential algebraic equation. And then that right-hand side is shipped off to the differential equation library. So that's a library written in Julia, a vast library actually of hundreds of differential equation solvers. So you can typically find your favorite solver in there, and you can even use Sundial's classical suite of solvers if you would like to do that. Typically, there is no reason nowadays to use Sundials, because you don't get some of the nice Julia functionality that you get with the native Julia solvers. But I don't know if that answers your question. Otherwise, feel free to ask again, and I'll try to refine my answer. All right.
Okay. You can email us if you have any questions as well. All right. Thank you, Frederick. That was very informative, and it was also very fun. Thank you to everyone who joined us today. We will be sending you a follow-up email that will include a link to the recording, so you can view this webinar later. And you can always reach out to us if you have any additional questions about JuliaHub. Also, please keep an eye out for our upcoming webinars, and feel free to join. Thank you, everyone. Have a good rest of the day. Bye.
Thank you.